Okay, hi Year 11. So this is the follow-up to the chromatography lesson from today. Just a little recap then. This is the chromatography paper and it's staying still, so it's the stationary phase. This is the solvent that we use, which could be water or ethanol. We need a solvent that will dissolve our substance, so it can be water, ethanol or whatever solvent, and this is going to move up the paper. This solvent is going to move up the paper, so therefore it's the mobile phase. So, separation in chromatography, this is a really important thing I want you to write now. Separation occurs because different substances have different affinities for the mobile and stationary phases. So a couple of words there I need to pick up. Different substances have different affinities. Affinity is how much you like something. So I have an affinity for chocolate. Remember that, end of term, love a bit of chocolate. Different substances have different likes, different affinities for the mobile and stationary phases. So what that means is if you have a greater affinity for the mobile phase, you will move further up the paper. You will move with the mobile phase. If you have a greater affinity for the stationary phase, you will stay still. You will not move as far. So stationary and moving. Alright then, so what we're going to be looking at in this little, so that's new for your notes. What we're going to be looking at in this little section then is what happens, what do we do with the results from this experiment? How do we calculate something called RF values? I'm going to teach you this very, very quickly, and then the rest of the learning is going to be done by going through these questions that you will have. And once we've gone through each of these individually, you'll be absolutely set with chromatography and it'll be fine. I don't think you're going to have any trouble with it. Okay, then let me just remind you of this. The solvent has got to be below the pencil line, so this is a pencil line. If it was an ink line, it would dissolve. The solvent's got to be below that. So let's just imagine then that we've put a little dot on here and it's risen up and it's separated out into two other dots like that. Okay, so I've put one dot on this line and it's separated out into two. What this tells me then is that this substance must have been a mixture because there were two dots. So one dot would be a pure substance. This is two dots. I can tell that this dot here has moved further than this dot. So the dot I'm pointing at prefers or has a greater affinity for the mobile phase. This has the greater affinity for the stationary phase. So we're going to look now at how we can use this data here to find out what these substances are. Okay, so on the next page I'm just going to draw that result on there. Doesn't really matter how you draw it, just draw two dots like that on your notes, and we're going to calculate something called RF values. Okay, this stands for retention factor, so how much these dots have been retained by the paper. So what we're going to do then, on this piece of paper, I'm going to mark on this line. This would be what we call the solvent front. And you might have seen that today in the lesson. That's how far the water rose up the paper, and I've marked that. And what I'm going to do, I'm going to work out the RF value, which is the distance the spot moves divided by the distance the solvent moves. Alright? So, let's have a little look. I'm going to get a ruler from over here. So in an exam you could be asked to calculate the RF value, and you can measure it in millimetres or centimetres. So I'm going to work out the RF value for spot A, and this is spot B. Alright, firstly, the distance the spot moves, I'm going to do from the middle of the spot, and it's to the line that it started on. Remember, everything started on this pencil line. So on mine, that is 15, 16, 17 millimeters. And the distance the solvent moves is 25 millimeters. 17 divided by 25. Plug that into your calculator. I haven't got a calculator with me, but that would be the RF value. I'll get my phone out to do that. And in the meantime, I'm going to multitask. I'm going to write spot B. It's going to be divided by 25 again, because that's the distance the solvent moved. Center of the spot, 1, 2, 3, 4, 5, 6, 7 millimeters. 7 divided by 25. So, getting my calculator out on my phone, taking me a while because it's the oldest phone in the world. There we go. So I'm going to do RF value is 17 divided by 25, 0.68. And then I'll do 7 divided by 25, 0.28. They are the RF values. And what we can do is we can compare these to known values in a database. And you look up these values, and as long as somebody has used the same paper and the same solvent as you, we could identify the materials from their RF value. So this is quite important. We can compare these to known values in a database. Please do realise that whoever did the experiment in the database, they had to use the same equipment as you, otherwise the spots move different distances. So anyway, let me just talk about, I'm just going to ask you a question. What do you think the biggest value for RF would be? Good question, good question. Well, the biggest value would be if it moved all the way up here, like that, and that would be, in this case, 25 divided by 25. The biggest value for RF is 1, and that would be a substance that moved all the way with the mobile phase, didn't stick to the paper at all. And if you go halfway, that would be 12.5 divided by 25. Halfway is 0.5, unsurprisingly. A quarter of the way is 0.25. So all these RF values, it tells you how far it's gone up the paper. 0.68, it's about 2/3 of the way up the paper. That would be 0.66, wouldn't it? So that's all these RF values tell you. So this is on higher and foundation, the ability to calculate RF values. Cool, and we can compare to values in a database. So what we're going to look at now is some questions. And in those questions, we are going to be tested on things like pencil lines, solvent below the pencil line, putting a lid over the top, and lots of different things, talking about stationary and mobile phases, and also about RF values. So let's get on with it and see what sort of questions come up in the exam. Okay, so you can work along with me on this. This is absolutely fine, or you can do these questions on your own. I don't really mind. If you fancy doing one of these questions, just pause the video, but I'm going to go through it and model how I would do it. So chromatography can be used to separate components of a mixture. A student used paper chromatography, and that just means they've got paper down here, to analyse a black food colouring. The student placed spots of known food colours, A, B, C, D and E, and the black food colouring on a sheet of chromatography paper. So they've got known food colours along here, and then the black one is here. Right, what it says, they've dipped it in a solvent. There's a start line drawn in ink, and there's some black food colouring on here, and these are going to be used for comparison. We'll see the results in a minute. The student made 2 errors in setting up the apparatus. Yes, they did. Identify the 2 errors and describe the problem each error would cause. All right then. Well, they've got a start line that's been drawn in ink. So there's my identification, start line drawn in ink, and the problem it would cause. This ink line would dissolve in the solvent. Okay, it would dissolve, it would wash off. Next problem is they have put the solvent above the pencil line. So the solvent has gone above the pencil line. And that would also mean, that the samples would not rise up the paper, they would simply wash into the solution. So we'll have a little look at what it says. We're going to talk about, try to find out about their language that they use. So the start line was drawn in ink. I noticed that. So the ink will run or it will dissolve in the solvent. All right. So I wrote that. It will dissolve in the solvent. When it says it will run, it will like smudge up the paper. They put the spots underneath the solvent, or the start line was under the water. It will wash off the paper. It will dissolve in the solvent. Okay? So if you dunk an ink line underneath the water, it won't rise up the paper, it'll just wash off. So all the samples will just wash off. Okay, so they were the two mistakes that they made. This is a very common type of question. They'll give you a diagram like this and they'll ask you to spot the mistakes. Right, on to the next page then. Here are the results. A different student set up the apparatus without making any errors. The chromatogram in diagram 2 shows the student's results. What we can see here is that substance A has got one spot, one spot, one spot, one spot and one spot. So all of these substances A, B, C, D and E were pure colours. And then this is the black food colouring. And the black food colouring is split into 3 dots. This dot here matches with colour A, this dot here matches with colour E, and this dot here doesn't match with any of the colours. So what do the results tell you about the composition of black food colouring? Well, the first thing it's telling me is it's made of 3 separate colours. Now that often isn't enough to get you the mark. So I'm going to now say one of the colours is A, that one. One is E, and the third is none of A to E, as in we don't know what the third colour is. I think that's what it tells me. So what do the results tell you about the composition? It is made of 3 separate colours. So it's a mixture. Let's go with it's a mixture made of 3 separate colours. One of the colours is A, one is E, and the third one is none of A to E. Let's again have a little look at the back. Fairly straightforward idea. So if it moves the same distance, it is the same substance. So it contains A and E. Did I write that? Yeah. One is A, one is E. And another one, which is unknown. Cool. If no other marks awarded, an answer saying it's made up of 3 colours would gain 1 mark. So it wasn't just enough to say made up of 3 colours. It contains A and E and another. Alright then, use diagram 2 to complete table 1. Distance from the start line to the solvent front. Alright, so that's that. And it wants it in millimetres, so that's 43 on my one. And distance moved by food colour C. So I'm going to go to the middle of that, 17. Now, don't worry if your answers for these are different to the ones in the back, because it depends how big I've printed it. The RF value, though, should be the same, because the proportion of how far it's moved compared to the solvent will be the same. So I'm going to do 17 divided by 43, and that will give me an RF value. Have I still got my calculator open? I have now. 17 divided by 43, 0.39. 5. Did it ask for sig figs? No, it didn't. So it might be 0.40. What would it go? 0.40. The reason I said it might be 0.40 is because I've done it to millimetres, 2 significant figures, so I would have rounded it to that. Alright, next one. So that was RF value being used. Table 2 gives the results of chromatography experiments that were carried out on some known food colours using the same solvents as the students. So this is the data table that they've got using the same solvent as the students. So there are some food colours here: Ponceau 4R, Carmazine, Fast Red and Erythricine. These are the RF values for these 4 known colours. Which of the food colours in table 2 could be colour C from the chromatogram? Well, we've just worked out this value of 0.4. So, clearly, we're looking for a match. Fast Red, because it has the same RF value. 2 marks. Surely that's got to be it, right? Fast red, same RF value. Okay. 2 types of chromatography are gas chromatography and paper chromatography. Now, we're going to do that one later, topic 10. Okay, we'll talk about the advantage of gas chromatography and paper chromatography. Next, question 2. This question is about mixtures. Which substance is a mixture? Well, gold is pure, methane is a compound, nitrogen is a single element, air is a mixture, and we've done that. It's 80% nitrogen, 20% oxygen, etc. Food colourings are often mixtures of dyes. What name is given to mixtures that are designed as useful products? Formulations. Okay, so that's how formulations can get asked. The student investigated a purple food colouring Y using chromatography. The student compares Y with dyes A, B and C. So very similar to the last question. So here are some individual dyes. These are probably going to give us individual spots, I imagine, and then Y will be a mixture. Let's have a little look. Start line, draw in pencil, solvent. Okay, all looks pretty good. Chromatography involves a stationary phase and a mobile phase. The mobile phase is the stuff that moves up the paper, which is the solvent. Stationary phase will be the paper. So this is a foundation paper. All right, next. What 3 conclusions, so there's the result, what 3 conclusions can be made about the dyes in food colouring Y? What 3 conclusions can you make about the dyes? Alright, so food colouring Y contains dye C, it contains dye A, and it contains another dye which is neither A, B or C. I think that'll probably be it, won't it? If we're looking at the same sort of marking as last time. Allow contains 3 dyes, contains 2 known dyes, contains an unknown dye, contains 1 known dye, 2 unknown dyes. Alright. Right, same sort of idea though. It did seem to allow the fact that it contains 3 dyes as one of the answer for this one, so that's maybe the foundation level bit. I don't know, but what am I getting from this? Food colouring Y is made of 3 different dyes or 3 different colours. I know that it contains dye C, it contains dye A, and it contains an unknown one that is neither A, B or C. You're getting the idea? This is very, very common sort of thread with these chromatography questions. In a different experiment, a student recorded these results. So the distance moved by the dye is 60. The distance moved by the solvent is 80. Calculate the RF value, easy peasy. That's foundation level. Food colouring is a formulation. What is a formulation? Okay, it is a mixture made for a specific purpose, made to a recipe, or with known amounts or known concentrations of each part, but it's whatever our definition was from the book. Explain how paper chromatography separates the dyes in a food colouring. Do not give details of how to do the experiment. So, the dyes in a food colouring. Each dye will have different affinities for the mobile solvent and stationary phases. The paper therefore will move different distances up the paper. Let's see if that gets me the answers. 3B. 3B. The dyes are distributed differently between the stationary and mobile phases. Different forces of attraction. I've written the word affinities, which is definitely allowed. Affinities. They're distributed differently. Dyes have different solubilities, different forces of attraction for stationary phase and mobile phase. We're going to go with different affinities, please. The dyes have different affinities for the mobile and stationary phase, so move up the paper at different speeds or move different distances up the paper. Yeah, different distances. We're not really bothered about the speed. Okay, so they'll have different affinities for the mobile and stationary phases, therefore we'll move different distances up the paper. Absolutely. Please use the word affinities. That's absolutely fine. I want it taught that way. Explain how the student could tell the chromatogram that the food colouring from the chromatogram that the food colouring contained more than one dye. If you've got more than one dye, you will have more than one spot on the chromatogram. Now then, why is that going to be 2 marks? How could the student tell from the chromatogram that the food colouring contained more than one dye? I don't know how to get the 2nd mark here, so I'm going to look. This is how we revise. This is how we use past paper questions. What are they after for that 2nd mark? Because it have different dots. Wow. In a vertical column. Oh, that's so annoying. How could the student tell the chromatogram that the food... I'm trying to explain this, right? More than one spot on the chromatogram I thought would have been enough. But apparently this year, more than one spot in a vertical line. So there we go. I've used the mark scheme and I'm now aware of weirdness. Let's just deal with it. This is how we've got to learn. By doing questions and by looking at mark schemes. Explain how the student could use chromatography to identify unknown dyes in the food colouring. How could the student use chromatography to identify unknown dyes in the food colouring? Alright, so I could, what could I go with here? I could work out the RF values for each spots. I could then compare to known values in a database. Could I do that? I mean, again, I haven't seen the answers. I could do that, but why is that worth 3 marks? Or I suppose I could do a chromatogram with known dyes across there and then do my one for comparison. Okay, so triple. This is what I'm talking about. I don't know exactly what it wants here. So what sort of thing does it want for 3 marks? Either of these would work as an idea. So I could run known dyes and the food colouring, which was this idea. There's the food colouring, there's ABC, there's some known dyes. Compare the distances moved, or compare RF values. Okay. So you can identify those that move the same distance, or you can identify those that have the same RF values as known dyes. Alright, so it wasn't wanting me to compare to a database, it was wanting me to describe this sort of experiment. Right, so there you live and learn. So we've seen this type of experiment up a couple of times where you have known dyes and then you have your unknown sample here and you compare to see which substances move the same distance as known dyes. So there we go. I didn't do it well. I don't really care right now because I'm teaching you how to learn. That's the key bit. I'm teaching you now what do AQA look for when they run these questions. So compared to a known value in a database, this clearly would work, but they were wanting me to describe this sort of experiment, which we've got down here. So they're very keen on this style of experiment where you've got known dyes and then you've got your unknown mixture here. So let's have a little look. What colours are in black ink? So there's black ink. Black ink contains red, blue, and an unknown. I think I'm learning what AQA want. Red, blue, and an unknown. This is question 4A. Come on, be red, blue, and unknown. Red, blue, and unknown. Red and blue and unknown. I'm getting better, aren't I? Are you noticing that? I'm learning by doing loads of questions what they're after. You need all of them for the mark. Okay, cool. Suggest what colour is the least soluble in the solvent. Give a reason. The least soluble. So the solvent rises up the paper. The solvent is the mobile phase. So this colour moves the least distance. Red, because it moves the least distance. Red travels the least far, moves the least distance. Okay, getting better. Use the diagram to complete the table below. Distance moved by green colour, distance moved by solvent. Work out the RF value. Distance moved by green colour, distance moved by solvent. Work out the RF. Wow, look at this. 4 marks. What a gift for just using the ruler and by This must be foundation, right? Must be a foundation paper. Right, that one's done. Question 5. We're nearly there. This diagram shows a chromatogram for food colouring. How does the chromatogram show that the food colouring is a mixture? More than 3 dots in a vertical line. Got you. That's only 1 mark, but I'm going to say that. More than 3 dots in a vertical line. You know why I'm saying that from before? Good. The student makes measurements for spot C. Calculate the RF, 7 divided by 39. Give your answer to 2 sig figs. Don't mess that up. Next question. Plan a chromatography experiment to investigate the colours in an ink. And this is a 6 marker. Alright, and I want to see this one done by you guys. So, this, I want to see written out in full, please. We need to investigate the colours in an ink. So what I'd be wanting you to describe then is an experiment whereby you've drawn a pencil line and you've put it in some solution, in a beaker, with the solvent below the pencil line, and we're going to stick a lid on. The lid stops evaporation. Alright, the lid stops evaporation of the solvent. I'm going to investigate the colours in an ink, so I'm going to put my mixture, my ink on here, and I'm going to put some known individual dyes on there. That'll be a nice idea. I'm going to run it till it gets almost to the top, and then I'm going to compare the dyes in my ink against the known dyes. I could calculate the RF values of the dyes as well and compare to those in a database. I'd put that in as well. So I want to see that you've written that in. You've actually written that answer. Let's have a little look then. Run the known dyes with a food colouring. So I did that. Oh, hang on, that's the wrong question, isn't it? Where are we? Question 7. Okay. Put dots of known colours and a dot of the ink on a pencil line in chromatography paper. I described that. There's my ink. Place the bottom of the paper in water, making sure the start line is above the water. I mentioned that. Leave for the solvent to rise up through the paper, not all the way to the top. When it's near the top of the paper, remove and leave to dry. I didn't mention that. Compare the positions of dots for the known colours with those from the ink. I did mention that. Alright. And there's a levels 5 to 6 part up there, which is missing off my paper. There it is. The plan would lead to a valid outcome. Okay, so you'd have to write that, but this is where we hit about the solvent below the line. This is a pencil line. Don't let it run all the way to the top and stuff like that. That's a classic question, comes up every year. This is a required practical. Right then, this is my favourite question because it just raises so many questions about horse racing and betting and things like this. Racehorses may be given drugs to improve their performance in races. I think it maybe as in they could be given drugs, not they're allowed to be. Oh yeah, this is illegal in the UK. After races, urine samples are collected from the horses and these samples are tested for drugs. Chromatography is one of the tests used to identify drugs in urine. The diagram shows a chromatogram. Proper interesting question. Here is the urine sample from the horse there. So we can see that this horse has got things in its urine. And let's just have a little look to see what it's got in its urine. Right, so it's got this substance here, and we don't know what that substance is because it doesn't match with caffeine, cocaine, and ketamine. This substance matches with cocaine. I love this question. This horse has been given cocaine, and it's got another substance in there that we don't know what it is, and it definitely hasn't been given ketamine, which is a tranquilizer, so it's a good job. So this is a horse who's taken cocaine. How do we know that sample 1, this one, was a pure sample? 1 spot only. Okay? We don't, yeah, okay, let's have a little look. Calculate the RF value for cocaine and give your answer to 2 sig figs. It tells you the RF equation, which is a bit of a joke. Distance moved by substance divided by distance moved by solvent. So you go halfway across there, there's cocaine, you'd read to that, you'd read to there. It's pretty straightforward. Give 3 conclusions about the urine sample from the horse. Okay, 3 conclusions. It's a mixture with 3 substances in. it contains cocaine, it contains 2 unknown substances which are neither cocaine, caffeine or ketamine. Alright, let's have a little look then. Made of 3 substances, 2 are unknown, 1 is cocaine, 3 marks. Alright, so there you go. Have an image of a cocaine fueled horse in your heads. That is chromatography. Alright, what do they like to ask us? They love the idea then of known samples against a mixture. The weird thing, they like to say more than 1 dot in a column. They like us to compare the dots to known values, and they like us to calculate RF values. Alright everyone, that is chromatography GCSE done.